that you have given me an opportunity to be here to give you a small lecture on the modeling inversion techniques in solving the industrial problems. In fact, industrial problems are very many and they cannot be defined just by saying some industry problem or environmental problem or mathematical problem or engineering problems, but there is a chain of the problems. What is required is to understand and interpret the data which we are today getting from the various sources and from the various measurements. So here I will be presenting you a very important research topic, that is the inversion technique using the integral transforms, which is the need of today's world. Why? Because what we are really getting is tremendous data. This data, we are unable to understand what this really is coming from. We know that this is the zone of the data, but we do not know where the culprit is. Sometimes, even in the, for example, suppose there is a radioactive source which is lost mistakenly, and one has to discover where this source is lying, how big it is, and what are its dimensions, location. It is very tough. So what you do, you take a GM counter and you measure the radiation intensities, and from that map you try to locate wherever the intensity is very much, you say the location of the source may be there. And when it comes to find the sizes, sorry, it is very difficult. Why? Because we do not know how to interpret this data. We know now the location, approximate location, but in order to pinpoint, to know the parameters and the size and the shape and the location and the depth, we have to do a lot of rigorous analysis, and for which you require a lot of mathematical techniques. And these mathematical techniques range from simple algebra, differentiation, integration to the integral transforms, which is really the gamut of the main lecture today which I am talking about. So when we talk of the modeling and inversion, I will be explaining you what is the model and inversion and what are the kind of problems. Next slide please. So this is the kind, go back. This is the kind of a thing I have written, that integral transforms play pivotal roles in the inversion of such kind of problems. There are many problems. The one which I have given is only an example. It is not the only problem. So there are many scientific, technological, industrial, computational, physical, geophysical, hydrological, and many more kind of environmental problems. In this work, a review of the various transforms are presented in order to know the thrust of the present day's need and the requirement of the research, where the mathematicians should apply their whole brain to understand the need of the world. Sorry. A few examples I will be giving about Fourier, Laplace and Henkel different transforms, and then I will be talking about their application. And you will find very interesting that these are not just related to mathematics or physics or engineering. They are related today on the medical technology also. Because medical technology, we go and we take our CT scan or we take the MRI, we feel, oh, this is all. But the whole physics, whole engineering, and the whole data which is being interpreted in the form of those pictures is very tough, and that is basically is done nowadays by software, where many transforms like radon transforms are used to interpret these kind of things. Next slide please. So I said, why the integral transforms in this talk? Because many mathematical applications, their use has become predominant in all advanced studies and research areas of the industrial problems. Keeping these things in mind in this lecture, my goal has been to provide a systematic exposition of the basic properties of the various integral transforms with their applications. And some boundary problems also I have just touched upon. In addition, some integral transform and calculus I will be talking may not be very important. Please, next slide, please. Now, question arises as the topic is, what do you mean by the inversion method? Now, inversion of what? And that inversion is applied where? So, this is the case of simple estimating the model parameters from the observed data. So, when we are talking of the data, we should know what is the kind of the model you have in the mind. And that model, what is the kind of the parameters it has got. As I just gave an example of a radioactive source, I can give this kind of example of a hidden body under the ground, and you are measuring gravitational field on that. By the gravitational field, you will know where the body is lying, but you will never know how deep it is, how big it is, how thick it is, how rough it is, and so on and so forth. So these are the kind of the parameters you would like to know. Next one. Now, in this particular case, this is the general view or flow chart of the inversion problems and the kind of the forward problems. So as you know, as I told you, the basic input data and inputs which you are available with are the data uncertainties, data and uncertainties, and then the governing equations, because whatever the phenomena we are talking about, that kind of a phenomena which may be having some of the governing equations and some prior knowledge and assumptions. Because for example, when we talk of the kind of a gravity, as I gave the example, we know what is the kind of a location, what is the kind of terrain, or kind of the, suppose we take up remote sensing, when we are talking of the weather, we know what is the kind of conditions, like clouds are there, temperature is there, then hills are there, vegetation, and so on and so forth. So some prior information. Now inversion implementation. There are two approaches. See, there are two things. You know the actual model, actually suppose kind of a body which you are looking for, you know its dimensions and you want to know the response. But since you have given the model values, I mean those parameters well known in unknown form, so you are simply solving like a algebra. But question arises. So this in the forward problem, you do the discretization, you do the simulation, and then you fit the model and try to know the picture. But the difficult situation arises when you have only data and you have some information. It is like a job of a detective, that something is done and then you have to trace out what is the main cause of the whole thing. So therefore, this is the inversion, which is my topic also, that in inversion, you do the discretization, as here also. Here you do what is called regularization. What is regularization? I will be telling in the next slide. Then the use of the integral transforms appear here, and by that integral transformation, then you go to the numerical simulation and then you optimize the parameters. So having done all this, what you get, whatever the data you have done, some evaluations of the parameters, then you try to interpret. And when you interpret, you require the conditions all around. That is what I was talking, that some prior knowledge. Next one. I was talking about the kind of a hidden body. Suppose this is the hidden body under the ground and you want to know what are the kind of the depth and then sizes and things like that. What you will do, you will collect the data over you will make a grid, and at every location you will be finding the value of that gravitational field or magnetic field or electrical field, whatever. So this is the data collection from measuring the instrument, the measured data, and then you try to go for fixing some depth, then you just small parameters you decide, so they become your unknown. Next one. So after doing all this, just in the previous slide as I have told, develop a relationship between the model, I call model as M, data as I call matrix T, and then parameters I call the matrix P. Then equation becomes like this: matrix of N is equal to the matrix of data and the matrix of the parameters which are unknown. So in order to know unknown, you inverse this matrix. So this matrix comes here, and so you go for a solution. Now question arises, do the solutions always exist? It is not necessary. It is not necessary. Many a times solution does not exist, and the data which we are getting is, the response of the system, or the response of the body which we are looking for is so low, and the error is so large, it becomes very difficult. Sometimes it becomes impossible to find what you call the solution. Very popular example I will give. Suppose thousands of people, hundreds of people are there, and some murder has been committed, and all are having same dress, same kind of all hats and all that. To find the culprit in this kind of a crowd, it is very tough. Why? Because all this error. Because we are not able to point out one strong signal by which we will go to discover. So, as I said, solution, it should exist. Linking the physical phenomena to the equation, then finding the inverse of the matrix, find then P, provided as I said. Next one please. Now, so linking the equation, then that is a system which you have evolved, then you find D inverse, you apply all the mathematics, computer techniques to find the matrix inversion, and then again you come back to the this multiplication. You come with the kind of the large number of the linear equations which makes it finally that matrix, and then from this you try to find the matrix P. Next one. Now, but the solution of the inverse problem divides it in two following categories. As I told you, there may be and there may not be solution existing. So there are problems. Actually, there is those which are well defined, we say this is a well-posed problem, and those which are not well defined, we call them ill-posed problem. But question arises, what are these two categories? Next one. So mathematically, if the solution exists, the solution is unique, and the solution's behavior changes continuously with the initial condition, we say this is a well-posed problem. And next one, in the absence of these three, we call that an ill-posed problem. Now please remember, the forward problem is a very well-posed problem, while inversion problem is mostly ill-posed problem, and therefore tough kind of numerical mathematics, regularization, and so many kind of technology, mathematical technology is required to do that. Next one. Now, sometimes you have lot of data and you know the parameters, but you have more data than the parameters. Suppose you have got only few parameters and you have thousands and thousands of data. How would you determine the parameters? For example, there is a kind of we see that today climate change is taking place and the ice is getting thicker. Sometimes somewhere people say Antarctica has become melting, and then that's ablation. Ablation means removal of the ice. So things are happening. Now question arises, what is the rate at which this ablation is taking place? Data is in millions. This is a very big data, but you need few parameters. At that time, multiple regression, principal component analysis, and cluster analysis are very good. So this is the next one. Now this is a biochemical kind of the example for the multivariate only. Next one. Now how to proceed? As I told you, discretization of the continuous model is very necessary. Regularization and simplifying and linearization of the complex phenomenological equation is also very necessary. Next one. Now, as I said, continuous model has to be discretized so as to see that you keep a control over the numerical instability. Regularization, as I told you, to bring some kind of a stable algorithm so that you can apply the computer simulations and you can solve the problem. Very famous regularization, which is Tikhonov regularization, is applied. Next one. These are the simple examples. Least square method, or the solving the, by the Tikhonov or linearization of the complex equations is, these are the simple regularization techniques. Next one. Now, inversion scattering method, in particularly in physics, this started approximately around 1972. Though there are papers, if you'll find, in 1950s, but it took the shape after these equations were used by the analogous methods. That means somewhere some similar kind of equations are there and similar technology you are able to apply so as to know the what are called the unknown parameters. Next one. As I told you, applications are many. They are, as I told you, in quantum scattering, weather predictions, oceanography, hydrology, petroleum engineering, medical tomography, CT, MRI, and so on and so forth, remote sensing, and all that. Next one. Quantum scattering. Suppose this is a nuclear matter, and this is the incident beam, just like in LSC experiment in the Geneva, as we Switzerland, we have found certain laboratory. Now this is the incident, this is the scatter, this is the passing through. So this is the matter about which we have to explore. So you have the observations, and then using the inferences, you find what you call the stable by using the scattering, the inverse scattering. Next one. Next you can go. What I was telling, useful transforms in the various problems are mostly the most utilized transforms in the world, in all the mathematical and technologies literature. You will find Fourier will stand first, second will be the Laplace, Henkel may be the third, and these are used very deeply kind of in theoretical physics, astrophysics, and so on and so forth. Next one. Now, genesis of integral transforms normally dates back from the Fourier's beginning, when he started what you call the sine, the periodic series, and therefore, but of course, Heaviside added to that, and these kind of expressions, which were first time started by the Heaviside. Next one. Well, this is only to tell that Henkel transform has some Bessel functions. Now Fourier has got the sine and cosine functions. Hilbert has simply the phase changes of the, and so on. Next one. Well, very well, this is established that Fourier transform utilized to put the data into two domains. One is called time domain. Some other data is called in the frequency domain, and you know, sometimes your imagination fits well into the frequency domain while somewhere in the space domain. Mostly the data today, all these you use what you call these mobiles, smartphone, they are all, what is done, basically the power spectrum is analyzed, and you remove those frequencies which are disturbing the band which you are using, and therefore, so every time these kinds of transforms, though now better transforms have come and they are utilized, but still they stand basically. Next one. Now they have started what is called wavelet kind of transforms. They actually, this is started basically from geophysics, and then later on started being utilized in the communications. Next one. Then there are transforms, well, next one. Next one. Yeah, Laplace transforms in the engineering problems are very many, and they, as you know, they are not only used mechanical vibration analysis, electrical signals, and but nowadays most of the branches are using Laplace, and you will find hundreds of books on the inversion of the, and there is a big software and SPSS over the what you call the Laplace transform, and which is very utilized, very much utilized in various inverse problems. Next one. In medical science, as I said, when you are talking of the CT scan or the tomography, both are used, radon and the wave-led transforms. They are special because in this lecture we cannot go into the mathematical details, but just to, as I told you, I am just giving you overview what are the kind of transforms which come to invert the data, because whatever the data you are getting in tomography, in order to know the structure, in order to know the inside information, we use these kind of. Next one. Next one. Of course, this can always be proved that Laplace transform is the form of the Fourier transform. So just using the complex function, you can change that. Next one. Next. Significance of the Fourier integral theorem is very much. I will be showing in few the pictures later on. Next, proceed. Gamma transform is another transform which came into the mechanics, the quantum mechanics, and this transform started using what is called time frequency, time frequency kind of plane. They also call what is called time frequency atoms, because mostly you will find that the spectrum or the spectrum which is available, so small windows when you are being utilized, and then you talk of the uncertainty principle. Gabor, the main British physicist who discovered that transform is useful nowadays in studying these kind of studies. Next one. Wave-led transforms is very much applied to the seismic signal analysis. Seismic. This is seismology, and seismics are different. When you are using by the vibration of the system, you use what is called seismics. So in order to experiment, in order to explore what is called oil explorations, they use tremendous seismic studies, and the instruments are there, and not seismology I am talking. So there you will find wave-led transforms. Next one. Hilbert transform and Stiglitz transforms are very much used in mathematical physics and the engineering and so on, but their more focus has been on the fluid and the aerodynamics and DSP and some of the electronics part. Next one. This is the kind of a picture I was telling when you talk of the Fourier transform. This is the actual waves or the pattern which you have found. That means this wave plus other waves all together. When you see in the time domain, this is a picture which is found. You can see this is one, this is another, but the combined picture is like this. But the same thing if I see from a different frame, you see, if I see from this, I see one picture, that is this frequency only. When I see this, you see, I get a picture. It's like a projection. When I stand like this, my head is there, but when I stand here, my nose will also come on the screen, because the angle through which you are seeing is very important. It is the angle through the time domain and the frequency domain on the basic kind of the significant kind of approach, of the Fourier transform. It is the angle by which you change the look of the whole basic data. That is the main constituent periodic function. Next one. This is Abel transform. Abel transforms is used mostly in the kind of the ionic studies, I will tell you. Next one. Now, this is the power kind of way, This is a Hilbert. Now, this is I was talking another transform. In Hilbert, this red picture is the one. You can find better peaks than the original data. Now, Hilbert transform has one quality. This changes the phase of the data by 90 degrees. Again, if you apply the Hilbert transform, again it will change by the 90 degrees, so 180 degrees. So you can have the different phase and therefore the different discretization. Next one. This is the One which I was talking, this is the Abel transform. This is the basically this is operated on this kind of a function, and this is the picture. And this is I will give you the next one. Hilbert transform. I just told it is one of the transform. I will show you the mathematical form next one. There is one another Millian transform, which is also kind of the Laplace transform, which is the, and therefore it is connected with the Fourier. So the kind of this one gives this picture, another gives this picture, and well, I am not focusing on this, just for example I brought. Next one. This is the, as I told in the case of the Fourier, these are this plus picture is this. If you see like this, if you see like this, like this. And there will be many small frequencies which we call as the white noise. Next one. Next one. See, this is that Hilbert transform. This is a kind of the, this is the original data. And this is the data. Oh, just wait. This is the original data, which is when you take the spectrum. This is the envelope, and this is the original picture, and this is the data which is found after the Hilbert transform. You can see that there is a difference in the shift in the phase. This is by 90 degrees. If I do another one, this will come here, and so on and so forth. Next one. This is very visible. Next one. This is another square wave is there. When you apply the Hilbert transform, the picture becomes like this, parabolic, like this. So this is the original blue, and this green is the transformer. Next one. Next one. This is the Abel transform. In this function is operated with this kernel, and this is the output. Next one. So the one which I was talking, as I told earlier, so this is inverse. This function earlier this was outside, and when we find this is the inverse of this. Next one. Well, these are the kind of the data signal processing. As I told you, there will be a scattered field, and then you will observe, then there will be some transmitted, then receiver, then transmitter, and then scattering data, and then you process by all these methods. Next one. Next one. So this is the whole gamut of the Fourier transformation. You can see our mathematical this thing. I will be leaving these slides with your professor, and you can collect and you can see in detail what are these mathematical. There is no time to talk about all these details, but they are very clearly given in this slide. Next one. This is, I have explained earlier also, that all these together with this picture, if you go like this is the power spectrum, this is the frequency, the time domain. Next one. This is the Millian transform. As I told you, I can, with proper transformation, I can bring it into the exponential, and this can be brought nearer to the what is called the Laplace transform, though it has different applications. I will show one application. Next one. Well, these are the many functions, and their Millian transform. You can see this is table which is just for reference. Next one. Here, when you talk of some of the magnetic field, when they are measuring, those geophysicists are measuring magnetic field on the grid, this thing, and when they plot, in order to find a higher resolution in the data, because there will be a lot of changes, when the changes are there, it is not perceptible when you plot them. Graphically, you cannot find those finer changes, and this Millian transform does that. And this is what I was telling, that it is also expected that the inherent advantage of the gamma function in this would be present in the transformed anomalies, and this is observed since the transformed anomalies are bounded by two asymptotes. That's all. Next one. So the resolution of the potential fields, magnetic field or the gravitational field, we call that potential fields, the resolution enhances. So it is very useful in that. Okay, next one. This is the kind of the data, some continental data I have got, and this is the gravity, milligauss it is called, and these are in the direction of this is the how many kilometers. So this is the kind of this thing. So when we apply the Marine transform, we are able to find the structure below the ground much better than other kind of methods. Next one. This is just I have given those who are interested in the climate changes and the kind of thing. Next one. The gravity data, as I was telling, this is one observed, and then these data is trying to fit on that this thing using that inversion technique. Next one. This is the radiometric data. By the plane or by the ground, you measure the radioactivity, various kinds of fields, and then try to find the images. Those images are what you call you have to process, and then you find inversion. Inversion means you find the sources. So by that, when you narrow down, you will find some of the areas which are the main source of the most of the anomalies or the object. Next one. This is the seismic data I was telling. The seismic data is always down to the earth, deeper. So here in this, they use what is called the wavelet transform. Next one. Now dealing with the geophysical problems, similar as I have told some of the other time. So this is the process they apply. Next one. In remote sensing also inverse modeling, as I was talking that suppose there are clouds or they are kind of the air, wind and the dust level, then how to interpret how it is done in remote sensing. Again, these various Kalsman filter or Kalsman transforms and various transforms are used. Next one. This is what is very important. I was just talking Abel transform. Abel inversion, see this is the kind of a thing which you are getting. Laser beam comes here, ion optics is being applied, and then you will find this is the kind of the Newton sphere here, but the picture you are getting is ion image here, and what this is nothing but a Abel inversion, and this is the picture which you can interpret, and this is called the velocity map. Next one. Well, I am almost at the end of my lecture, and I want to tell you that this is all said and done, but carbon dioxide, which we are talking so much about the climate change and its influence, is also dealt by the integral transforms, and the data is inverted, and Volterra equation of the first kind is being applied in order to know the carbon cycles and the kind of the breakoffs from the normal data. Next one. So, in nutshell, the use of the integral transforms I have talked in this particular lecture, and I hope this will be useful somewhere to motivate you to do the research and apply your mathematical skills more than theoretical knowledge, but if you go to the practical, it will be very useful to the world, and this will generate what is called the inverse all around, but not all the inverse. Next one, all the inverse you see right from the beginning of the universe and till the end where we are today. Thank you very much. Next one, my special thanks. I will fail to rather do my duty if I do not thank Professor Madhu Jain, who thought of me to invite for this lecture, and I could prepare last almost a week, and I am very happy, madam, that you have given this opportunity to share my thoughts on this particular topic, and that too by the video conferencing, which if I were near on the platform, which of course I am happy that you have given chance by video conferencing, so that I'm saved on the hot sun nowadays. Thank you very much. And Palak, who is a very brilliant research scholar in the Department of Mathematics of IIT Roorkee, who has been very supportive in all, whether it is a slide preparation, whether it is a presentation or timing, and I must thank her also profusely. And thank you all audience and all listeners and all the dignitaries here. Thank you very much.